Let us now do exactly the same thing on a weakly consistent machine. So what was the problem again? The problem was to add n numbers in parallel, right? So that's always the case. So in the previous lecture, we added n numbers in parallel on a sequentially consistent machine. That was easy. So all that we did is that we initialized our partial sums arrays, and then so we basically did some initialization, then fanned out a couple of threads. Each thread computed a partial sum for a chunk of the array, and subsequently we wrote some code to ensure that all the threads are finished. We added the partial sums and got the result. So all of this was done in the previous lecture, which is the previous part, the second part of this chapter. Now this being the third part, we'll do exactly the same, solve exactly the same problem, which is to ensure that we are able to do the same, which is add n numbers in parallel on a weakly consistent machine. So what again is the difference between SCs, which is sequentially consistent, and weakly consistent? So a sequentially consistent machine, all the threads respect program order, which means that given a thread, it will have some load instructions and store instructions, right? So all the memory instructions complete in the same order as they are specified in the program of the thread, right? In program order. But in a weakly consistent system, this exact program order need not be followed, particularly when we are dealing with different addresses. For same address, of course, we need to follow, because cache coherence, so I should rather use the word coherence, memory coherence is always followed in all systems. They can have different consistency models, but coherence is always followed. And also what is called single thread semantics, which basically means if I wrote something in the past, I should either read that value or a later value. That is always followed. So that's the reason for a single thread, these things are not relevant. But especially when there are multiple threads, what can happen on a weakly consistent machine is like this, that if I'm writing x equals 1 and y equals 1, other threads might see this in a different order, right? So basically, when we are looking at memory operations to different addresses, not the same address, mind you, in that case, in a weakly consistent machine, an ordering per se is not guaranteed. To force an ordering, we can have a fence instruction here. So the fence instruction basically says that it will execute only after all the memory instructions before it in the same thread have completed. And once the fence instruction ends, only then will all the instructions after it in program order actually begin. So that's how you force an order. So why again are we discussing this? Well, so being a computer scientist, we cannot always rely on frameworks like OpenMP, right? OpenMP is great, but we should first know how it is written. Point number one. Point number two is that tomorrow, if you have a different kind of machine in which maybe you're not getting good performance with OpenMP, you might want to, directly program at the level of the machine itself. So that's why it's always good to know more about the internals of hardware as well as software. So let's see. Let's try to solve this on a weakly consistent machine, which is, almost all the machines support a model which is weak to different extents. But we are not in a position to discuss that. But let's assume that a machine is the weakest, right? Weakest means orders are not respected, but they do have a fence. So if we write code assuming the weakest possible consistency, it will always run on a machine where the consistency is slightly stronger. In a sense, some more orderings are respected. So basically SC, sequential consistency, is the strongest, and at the lower end we have weak consistency, which is the weakest. So high performance servers always have this, right? And SC is ideal, so nobody has it because it has a lot of restrictions. It's not possible to get very good performance with SC. So that's the reason if we write any program for this, it should run on all systems that are stronger. So without further ado, let's start. So we can declare our variables, partial sums, finished, the numbers array. So we've seen all of this. I'll just skip. We initialize all the elements and partial sums and finish to 0. Now, here is an extra instruction which we did not have in the code, which solve this problem for an SC machine. So what we want, the reason we want to have a fence here is before we start all the parallel threads, we have to ensure that all our memory accesses are done, right? All our memory accesses are done, all our initialization is done, and all the memory accesses part of this is done. So the only way we can do it is that we assume there is a function called fence. Okay, this is an assumption. In reality, the C language does not have a function called fence, but we can always write a function, and inside that we can have a fence instruction which is there. This is there in almost all instruction sets, but it need not be called fence. For example, in the x86 instruction set, we have something called lock CMP, compare and exchange. Or just lock exchange, and you can have two registers as arguments. But as long as the lock prefix is there, it pretty much works as a fence. So this assembly instruction can be embedded inside the fence function. But just to keep matters simple, let's assume that we have a fence function which has a fence inside it. So once this fence is executed, we'll know that the initialization is done, and all the threads can see the initialization. So, all reordering per se will be taken care of. Now let's start the parallel section. So here again we make the same assumptions as we did in the code for an SC execution. So you can go back to that slide set and see what this meant. What this meant is that we just fork off n parallel copies of this code, and each code gets its unique thread ID, which is a number which varies from 0 to n-1. So the same assumption we had in OpenMP, we have not changed that assumption per se. Now what we know for sure is that when we actually spawn off the parallel threads, all the initialization is done because we have had a fence after it. So we can now happily define our starting and ending index for, if there's a large array, we can look at the chunk that has been assigned to the current thread. So this will start at the start index, and it will end here at the end index. So we can just add all the numbers within this block. So we have a we have a for loop where we just add all the numbers and save it in partial sums my ID, which is the thread ID for the thread which is doing this. So different threads, of course, will have different thread IDs. So they will write to different indices of the partial sums array. So after this, once the partial sums array is done, this data has to be transferred to one more thread which will actually add all the partial sums. But it's possible that we might actually transfer, but some of these writes can get reordered in the sense that this thread will work fine, but the other thread might not actually see the latest update to partial sums, because maybe the message with the latest update to partial sums, that'll be a write message, will somehow or somewhere get stuck in the memory system. It might not reach the location. So as a result, we'll not get to see it. So I just want to reiterate a point one more time, without making it very boring, that there is never a problem in a single thread execution, in the sense that last time that partial sums was written, you'll of course have the value because you're doing a plus equal to. So it is never the case that a single thread will never perceive any kind of reordering. That will work correctly because the assumptions of coherence are there, and that will ensure that the last time we wrote to partial sums, that value is there over here, so we can just keep adding. It's only a different thread might miss some of these updates, That's the reason it is necessary to issue a fence instruction such that all the updates to the partial sums array, I mean in specific the last update, that gets written in memory to its memory location such that all the threads can see it. So after the fence instruction, we know that partial sums has been written to. So we set the value of done, in the sense we set the value to done, and we set finished my id is equal to 1, which means that the current thread has finished. Now what we want to do is that we have to check with a for loop that all the threads are finished or not. If they have, then we just add up the partial sums. So this for loop is easy. We have seen something very similar in the case of a sequentially consistent system as well. So what we saw over there is that we have a flag variable. We iterate through all the threads. If in any thread the finished flag is equal to 0, which basically means that the thread has not finished, so we set flag to be 0, and then we basically break. And so break basically means that we sort of break out of this for loop and we come over here, and after that we see that the flag is 0 because one of the threads are not finished. So that's the reason we go back. So we will keep on iterating this do while loop until every single time this if statement fails, this will fail when all the threads have actually finished. So at that time we come to this sequential section, and we read all the partial sums, we add them to the result, and we compute the final result. So one thing that is extremely noteworthy over here is how exactly does it work, and how exactly is it different from the OpenMP and the sequential version. So we have already seen how the SC version is different from OpenMP, but the main differences here are as follows. So we first have a fence instruction. So recall that we had done the same thing in an SC machine with a variable. So we read that variable, but since SC preserves the order, just seeing that a variable has been updated also guaranteed that the initialization is done. We can't do the same here. So if this is the initialization and this is setting some done variable equal to 1, and if another thread sees if done is equal to 1, it will sort of start executing. This is not good enough in a weakly consistent system. The reason being that it is true done can be 1, but maybe some of the updates here have actually not reached memory, right? So if here we are accessing some of this data, we might not actually get to see it. That's the reason the right strategy or the right approach is somewhat different and on a weakly consistent system. And the right strategy is something like this, that after doing the initialization, we put a fence over here. So the fence ensures that we are completely done, and after the fence finishes means that all the values here have been written to memory. So what we do is we start a new thread, and the new thread, whatever it reads, it will get the right value, right? That is one change. Then the other change is we write the partial sums to memory and we do a fence, and then we set finish to be equal to 1. So since coherence is a global property across all models, right? So since we are writing 1 to finished my ID, the completion axiom of coherence guarantees that ultimately all the threads will be able to see that finished my ID has been set to 1. Once they get to see that finished my ID has been set to 1, means that this instruction is executed. This also means that the fence is executed, because unless the fence would have executed, the processor would not have executed this instruction as a property of the fence. And the fact that the fence is done means that the partial sums has been written correctly. All right. So what we do here uh, is that we basically recall that we check for finished, but we could not have put the finished instruction over here. That would have been wrong, right? That would have been completely wrong, and I'll tell you in a second why. Assume we had an instruction here. That would have been wrong. The reason being that another thread would have seen finished my ID equal to 1. So let's assume that's the last thread. That could have proceeded just by seeing the status of this. But it's also possible that the last update to partial sums might not have actually reached memory. So that would have caused a problem and the computation would have been wrong. So, but what we did is we did something smarter. We put a fence between partial sums and finished. And since ultimately all the threads will be able to see this update because of coherence, once I see finished my ID to be equal to 1, I will be sure that the fence has completed executing. Otherwise, this instruction would not have executed. That's a property of the fence. Since the fence has finished, partial sums must have completed. An update to partial sums must have completed. As a result, I'll get the right value. That's exactly what I do over here. That here we check for all the finished flags, and only when all of them have been updated to 1 does this for loop finish without a break, and flag is 1. So this do while loop, we come out of it, and then we compute the result, which is guaranteed to be the correct value. So what are the main differences? Well, the main difference is two fence instructions primarily, right? Two fence instructions that we added. That is the primary difference. And the most important thing to keep in mind is that in any weakly consistent system, the most IQ intensive thing is where to place the fence instructions. They have to be placed at exactly the right point. Otherwise, the final result can be wrong. So this, up till now, what we have been presenting is more of a logical or a conceptual or abstract view of memory of what exactly it should be. So we defined coherence and consistency, looked at their properties, and definitely looked at some examples. Let us now consider a physical view of memory, which is how exactly the memory works, right? The internals. So let's define two terms first, a shared cache and a private cache. So shared cache is where one cache is actually shared by all the processors. So it's basically one large cache which all the processors can access. It's a monolith. A private cache is where each processor or set of processors, right, have their own private cache. So let's look at example A. In this case, the L1 cache is shared and the L2 cache is also shared, right? In this example, the L1 cache is private. So the L1 cache is private to each processor or each core, and the L2 cache is shared. And in this case, the L1 is private and the L2 is also private, right? L1 is private and the L2 cache is also private. So, this can be done. So they have different trade-offs. So let's see what the trade-offs are like. So let's compare a private cache and a shared cache. So if we just go back to the previous slide here, so we can see that, well, one advantage of a private cache is that a shared cache has to be large. And each single private cache can actually be small, because if one processor, is accessing a part of an array, that small part of the array can be stored over here. Another part of the array can be stored over here. And the shared cache, of course, has to save the entire array. But cache size scaling with size, it prefers smaller the better. So in that size, the area of a private cache, at least of each single private cache, is low, whereas the area of a larger shared cache is higher. In terms of speed, of course, smaller the cache, faster it is. And since this is one big large cache, it is slower. Proximity to the processor, well, yes, a private cache is closer to the processor, and a shared cache is farther because, well, a shared cache has to be equally close to all processors, which makes it further away from each individual processor. So in that sense, it's slightly far away. Scalability in size, well, this essentially means that a private cache cannot become very large. We'll see why. And data replication, well, data replication and complexity is something that we need to discuss now. So let's go ahead and discuss. So what happens is that when you have one shared cache, this is clearly the simplest design. So in this case, if I write to variable x, then no problem, I can go ahead and write to x. Then if processor 2 wants to read variable x, then what it will do is that it will issue a read instruction to variable x. It will get the value. If processor n wants to do it, it will do the same. But in this case, the situation is different. In this case, well, we need to design some scheme, but essentially where will variable x be stored? So variable x has to be stored somewhere, right? So maybe x is stored over here. So the first question is, how does processor 1 know that x is stored over here? There has to be some way of finding that out. Well, if processor 1 wants to write to x, it might end up actually creating a separate copy of x. So, there'll be now two copies of x, one here and one there. Now, if processor n wants to read x, who supplies it the data? Does it get this x or does it get that x? And how does it know which copy of x is more recent, right? So we will have many of these complexities, and we still have to devise a mechanism which will ensure that this ensemble collection of private L1 caches. Maybe let me clean the screen. We need to design some sort of a system that will ensure that this collection of L1 caches behaves in exactly the same manner as a shared L1 cache, observes the rules of coherence as well as consistency, any particular model that the processor follows. But for any external, he should think of a cache as a cache, which basically means a set of memory locations with values. Whether it is shared or it's a collection of private caches should be absolutely invisible to any external observer. And this means that these caches need to run some protocol such that they're able to behave in exactly the same manner as a shared L1 cache, right? So this will introduce additional complexity. Here again, all of these L1s need to look like a single shared L1, and all of these L2s need to look as a single shared L2. So this is complicated. We need to, as we shall see, we need to do something, but an external observer should be, I mean, unless he does something more, uh, any program should behave as if it's running on a simple system with one large shared L1 and one large shared L2. In fact, any program should not even see that. It should just see the memory system as a black box, where for every variable there is a unique address. You can write to it, you can read from it. The axioms of coherence are always preserved, right? This is always the case that coherence is always respected. In terms of memory consistency, well, there are different kinds of models, sequential, weak, and a spectrum of models between sequential and weak. So whatever be the model, that particular model is respected, right? Those are two things that we want. So in terms of trade-off, well, in private cache, it is possible that, in each one of those private caches in this ellipse, variable x can be there here also, it can be there here also. Then, of course, we need to do something to ensure that, we are able to locate the most recent copy. But yes, replication can happen. And in terms of complexity, well, the complexity is high. Because we need to have some method of providing coherence among caches, which is called cache coherence. Shared cache relatively complexity is low. And also, because we need to run a protocol, the scalability in size, which means that we cannot have a very large cache uh, comprising of private caches alone, because the complexity will become very high. So that's the reason, they are not very scalable in the sense they cannot increase to very high sizes. But a shared cache can. Of course, it will be large and slow, right? So that can. Also, there is this issue of access. So assume if we have 32 processors, and if each processor can send a read or write request in a cycle, we need 32 access ports, right? We need 32 connections. And 32 access ports is absolutely impractical because having 32 ports will make the area of the cache increase by 500 times. 500 is an overstatement, but significantly, right? Large enough, significant enough to make this design non-feasible. But since the traffic between L1 and L2 is significantly lower, because L1 filters most of the accesses, L2 can possibly be shared. But not L1 because it will have too many access ports. But L2, L2 only talks to L1 here and maybe talks to a larger L3 or main memory at the bottom, right? So what typically is done is that the L1 level typically has private caches. And here again, the main thing is access port. So if you have one large L1 cache, it'll be too slow. So we will not be able to also put it close to every processor. And it'll span the entire chip. So basically reading one value might take tens of cycles. So that's the reason we have these small, what are called sub caches or cache banks that are close to each processor, but they behave as if they are a large shared L1 cache. That's a separate issue. And the L2 cache can be shared. So since L1s filter out most of the requests, the L2 cache does not need that many access ports. So that's the reason in principle it can be shared. And that is typically also what happens in commercial processors. The L1 level has private caches, and L2 and beyond have shared caches. So from this trade-off table, it would also be clear that having a large L2 is fine because it's not accessed very frequently. So you'll have to look at different factors, hit latency and miss rates and so on. But L1 level, you definitely need private caches because the traffic is so high, right? A shared cache will not be able to support it. So let's look at shared caches first because it's simple. So assume a 4 megabyte cache. So it will have a massive tag array and a data array, right? So the lookup operation will become very slow. In addition, we might have a lot of contention because it will be necessary to make this a multi-ported structure as we just discussed. Multi-ported basically means there are many parallel accesses, simultaneous concurrent accesses in the same cycle. And more are the number of ports, more is the area and more is the power. So the solution that is a standard solution is that we divide a cache into banks or sub-banks, and each such bank is a sub-cache, a smaller cache. So let's look at some math. So 4 megabyte is 2 to the power 22 bytes. So let us have 16 banks. We can then use, sorry, not bytes, it should be bits. We can use bits 19 to 22, 19, 20, 21, and 22, 4 bits to choose the bank address, right? We have 16 banks, so we need 4 bits. So we can choose these 4 bits to choose the bank address. We can then access the corresponding bank. And so since 4 bits are set in a 32-bit addressing system, there are 28 bits remaining, so we can use that to access the corresponding bank. The bank itself can be direct mapped or can be set associative, doesn't matter. And we can perform a regular cache lookup. So the standard approach with shared caches is that to support multiple ports, what we do is that we take the entire physical address space and we divide it, let's say, into, in this case, 16 chunks. So we just divide it. And how do we know, which chunk a given address belongs to? Well, we can take a look at bit numbers 19 to 22. So these 4 bits will map to 16 separate banks. So the banks itself can be organized as a matrix. So let's say that, we have 16 banks, and let's say a request maps to this bank based on these 4 bits. We can directly send a message to this bank. So this bank will contain all the addresses whose bits 19 to 22 have a fixed common value. So this gives us, well, one way of multiporting is this approach where basically we are dividing the physical address space, distributing them among banks. So most likely multiple requests will actually go to different banks. So we can satisfy many such requests in parallel. That's the broad idea. Even though in the worst case, all of these requests might end up coming to the same bank, in which case there'll be a lot of contention. So in spite of this, in spite of this technique in shared caches, they are nevertheless slow. Let me maybe just go back and tell you why they are slow. So, well, look, these banks are distributed all over the chip. And let's say that there's a processor over here and it needs to access something which is there in this bank. Then a signal has to go from one corner to another corner and the response has to come back. This can take well over 50 cycles. So this will make it extremely slow. So that's the reason we want to keep most of the commonly accessed data close to the processor. So this will still not work at the L1 level. At the L2 level, it's nevertheless fine that we split the address space, map each segment of the address space to a bank, and spread the banks all over. So of course, given an address, a bank might be nearby, might be far away. And so we nevertheless we locate its bank, send a message to it, and get the data back. So the L2, so there are also other ways of kind of optimizing this latency. But at the L2 level, by and large, it's a fine idea. At the L1 level, we have to go for a private cache kind of solution. So the private cache solution is that let's consider the most common approach. Each processor has a private L1 cache which others cannot access, which is nice and close to it. And all of the L1 caches act, right? The processor sees this group of L1 caches, right? This collection of L1 caches as one large logical cache. Okay? So basically, it sort of appears to the processor and a hypothetical external observer standing outside the cache that this entire collection is exactly the same as a shared L1 cache. No difference at all. So the axioms of coherence hold. As I said, this set appears to be one cache. So what does one cache mean? So a distributed cache, which is our case now with private caches, needs to be perceived as a single array of bytes by all threads. So when can problems happen? Let's see. Let's assume that thread number 1 to the global variable x is writing 1, 2, and 3, and thread number 2 is writing 4, 5, and 6, right? So thread T3 reads x twice, and thread T3 and thread T4 also reads x twice in two registers, right? We're assuming these temporary local variables are mapped to registers. So is it possible that the pair T1, T2 reads 2 and 4? Well, that is very well possible because this instruction can execute, then this, and then this. And in the middle, first T1 will read this value and then T2 will read this. This is perfectly possible. Can T3, T4 be equal to 4, 2 if we ignore this result? Well, technically, yes. Because T3, the first T3 can read the value of this right, and T4 can read the value of this right. But now, are both of them possible? Unfortunately not, because we need to see the same order of updates for each address across all the threads, right? So that's the order axiom of coherence. So one thread cannot observe x to have first the value of 2 and then 4, and the other thread cannot observe the value 4 and then 2. This violates our order axiom, which we have discussed in a great amount of depth in the previous slide set. So this is absolutely not possible. So since the order axiom is violated, this problem, this issue, or this particular outcome is not valid. So any system that obeys cache coherence will not allow this outcome. But the question is, how do we ensure that this outcome does not happen? How do we ensure coherence? Is there potentially a problem if multiple threads read or write at the same time? Well, the answer is no. What are the things that we care about? Well, we care about completion and order. So we basically care about the order of writes to a single location. Reading is just fine. There is no problem with reading. So what matters is completion, which means the write ultimately completes, and the order of writes to the same location is perceived by everybody in the same order. Also, so that's the reason writes in a sense are more important. Now let's take a look at the third point, which is you will always read the same data as long as there are no intervening writes. And the reading of the order of reads does not matter, right? That's more important. Uh, so maybe I should add it over here that the order of read operations per se does not matter as long as there are no intervening writes, right? So that is important. So what we are trying to say is we are trying to ensure coherence, but we still have not figured out a mechanism. We are just looking at some broad insights. The insight is first writes have to complete and their order matters because the same order has to be seen by everybody. But between two intervening writes to the same address, the order of reads is immaterial because we will always get the value of the latest write. So what is the big deal with writes in a coherence, kind of in a system with coherence? Well, so writes need to have a global ordering, of course, with respect to a single address. And the global ordering means that all threads have to see them in the same order, again, with respect to a single address. So the way we can implement this is that we can acquire access to an exclusive resource. And then, so an exclusive resource, well, what's the definition? It's a resource which can be anything, which can be acquired by any one request, either read or write request at any point of time. So the idea here is let us designate a bus, which is a set of copper wires, as an exclusive resource, which means that any request originating from any thread can get exclusive access to the bus, but it's only one thread at a time. Furthermore, let's assume that the read-write request that has exclusive access to the bus can use it to transmit a message to uh, other caches in a distributed cache and thus affect a read or write. So let's look at this in some deeper detail. So what we are essentially trying to say is that we will have our caches. So let's have all our caches. And of course, one cache is connected to its processor. Let all of them be connected via a set of copper wires. And let's call this set of copper wires the bus. The bus itself is passive, but let's also have a bus controller which gives one of these caches, right? So it's a copper wire, so multiple caches cannot write to the bus in parallel. So it'll give one of these caches exclusive control. So what will happen is that each of these caches will request the controller for exclusive control. The controller will apply its own algorithms. And the most important thing is that one of these caches has to be given exclusive rights over the bus such that it can use it to transmit messages. So this will also ensure a global ordering with respect to requests because who got access to the bus when. What we are further saying is that the order of reads does not matter, but the order of writes definitely does matter. And the reason it matters is basically because everybody needs to see the same order for a given location. So what we shall see is that the mutual exclusivity. What is the meaning of mutual exclusivity? It means that the bus can be acquired by any one request at any point of time. That will help us. So let's take a look at the Snoopy protocol, which is exactly along the lines of the diagram that I was drawing. So this is, there are two broad methods of cache coherence, Snoopy and directory. Directory is slightly more difficult, so it is sort of a stretch activity for us. We will not discuss it as a part of this slide set, even though I'll just give you a little bit of an idea. We'll mainly discuss Snoopy because it's nice and simple. Directory follows the same overall concepts, but it's otherwise very different. So let's try to look at a very simple system where the private cache is L1 and there's a shared bus. So all the caches are connected to a potential multi-reader single writer bus. What does this mean? This means that if this cache is writing something on the bus, everybody else can see it and read it, right? So in that sense, it's multi-reader and single writer, which means that one of the caches writes. Which one depends on who has exclusive control over the bus. And then the rest of the caches read. So what we have been talking about all the time is that the order of writes does matter. That's important. Order of reads does not matter. And since the order of writes matters, the mutual exclusivity of the bus, which means that only one request can hold on to it for the sake of writing, will help us induce an order on the write operations, which is exactly what's happening here, that we have a set of copper wires. One of the caches gets control of the bus, so you can use it to write on the bus, and the rest can read it. The bus essentially can broadcast data, right? If one of the cores, one of the processors and it caches, if one of the caches writes to the bus, the rest of the caches can of course read it. So this is the broadcast capability of the bus. And also all the caches connected to the bus will see exactly the same order of messages, right? Because once you transmit, everybody reads it, so they will see exactly the same order. And also they will see all the messages. So this will also ensure that no message ever gets lost. Let us look at the write-update protocol, which is one of the simplest protocols for maintaining coherence among private caches. So we start out like this, that we tag each cache line with a state. So I'll just tell you what it is. So for every cache line in a uh, private L1 cache, so assume that we have different L1 caches which are private, but all of them together observe cache coherence and they need to look like one big coherent L1 cache. So what we do is that in each of these L1 caches, in the tag array, along with the tag, we store an optional state. Along with the tag, the optional state that we store can have three values. So it can be modified, which means that after getting this particular line, it has been written by the current processor. It can be shared, which means that it is not modified. And it can be invalid, which is I, which means that this particular line associated with this entry is not valid. Right, so we have three states, M, S, and I. So it's also called a MSI write update cache coherence protocol. So since we have three states, to encode them we will require 2 bits. So these 2 bits can be stored over here. So now when there is a write, what we do is that we broadcast it to all the processors. Alright, so if let's say all the processors and essentially all the processors and their caches. So what we do is that if there is a write in this cache, then we basically send it to all the other caches, right? And we are assuming that one processor has one L1, there's a one-to-one mapping, so we broadcast it to everybody else. So then all the caches inside this cache group will update their data, and they will thus see the same order of writes, right? Not just for one location, but across all the locations. And the main reason being that how will we broadcast? We will write it to the shared bus over here. So let's say since the shared bus can only be acquired by one writing cache at a time, so what we can do is that we can, if one cache writes, the rest will get to read it. Similarly, in the next cycle, maybe this cache will write and the rest of the caches will get to read it. So the order in which the shared bus is acquired will be the same as the order of writes. So that's the reason all the processors will see the same order of writes to different memory locations. So this is good. Now what we do is let's consider the case of a read. So as you can see, the order axiom will automatically get satisfied by this mechanism. And also if we ensure that if we are trying to write, we'll ultimately get the bus, then also the completion axiom will get satisfied. Now let us consider a read. So this should rather be a read miss, right? So basically if we're trying to read a data and we find it, so let's say the processor is trying to read some data and it finds that data within its L1 cache. So what it will do is it will directly go to the L1 cache and read that data. For example, if a processor is trying to read the value of variable x, then what it will do, and it will ask its L1 if it has the memory address containing variable x. If it has it, it will directly read the data. Otherwise, if there is a read miss, right, you're trying to read but you're not able to get it, then we broadcast the read miss to all the caches, again on the Snoopy bus, and we basically ask everybody if they have the block, right? So if any cache has the block, it sends a copy of the block, again over the shared bus. Otherwise, we are sure that this is not there with any of the other caches. So we basically read it from the lower level. So let's see what's the advantage of doing this. So let's look at at a slightly higher level. So what is essentially happening in this protocol is that it is possible that the same memory location will be there in multiple caches. So it is possible that, let me again clean it and redraw. So it is possible that if I have multiple L1s, if I have multiple L1 caches, it is possible that the variable x is also here, the variable x is also here, and the variable x is also here, right? It's a global variable, so there is a memory address associated with it. To ensure that all of these copies are kept up to date, if any of the processors writes to variable x, it puts that write on the shared bus, which is connected to all the caches. So this is the shared bus. So it basically broadcasts the write to everybody, so everybody gets an up-to-date copy. Now let's say the processor that is associated with this L1 cache, it decides to read the value of variable x, it is guaranteed to get the most up-to-date copy. So it will basically get the right value. However, if there is a read miss, which means we are trying to write, but we are not able. If there is a read miss, means we are trying to read, but the variable x is not here. So I should rather say read miss. What we would do in this case is that we'll broadcast a request to everybody. If any of the other caches has the data, then we are supposed to get it from it again via the bus, right? And then we can read. We can keep a local copy of X, so that's how multiple copies get created, and then we can read it. So the advantage here is that so one advantage of cache coherence always is that we can get the data from a sister cache, and sister caches, different caches at the same level. Also, it will be incorrect to actually go to the lower level and ask the L2 because a more up-to-date value might be there in another L1 cache. So given the fact that this basic protocol has been explained, which is very simple, if you want me to explain in 2 lines, the 2 lines would be, when you are writing, send the write to all the processors. When you are reading, if you find the value in your local cache, take it. Otherwise, send a read miss to all the other caches, sister caches. And if anybody has the block, take it. Now, while evicting a block that has been modified, So basically, when you are evicting a block, the block can either be modified or unmodified. So if it has been modified, let us write it to the lower level, which in this case would be L2. Otherwise, well, why do we need to write it to L2? Well, there's a simple reason. So let me again do a little bit of cleaning. So what we have, at least in our current example, is that we have an L1 cache, then we have our shared bus, and we have our L2 cache. Now assume that we are trying to evict a block, the block that is containing variable x, we are trying to evict it from L1. So if the block is not modified, so if the block is unmodified, then of course we can throw it out because an up-to-date copy will always be there in the L2 cache or at a lower level. But if the block has been modified, then and we just cannot evict it because it has to be written down to a lower level. And at this point, we are not really sure if other caches, other sister caches have another copy of the block. So instead of asking them, it's a better idea that if the block is modified, then we directly write it to the L2 cache, right? So this ensures that all our modifications at the L1 level get reflected at the lower level whenever they have to. So let's look at a simple state diagram. So this is a state diagram of a cache line, right? So we recall that in the tag array, along with every tag, we add an additional state, which is 2 bits to encode 3 states, M, S, and I. Right, S, so I should rather call this ST, right? ST for state. So let's see. So initially we start in the invalid state. Then let's say that we get a read miss, which means we're trying to read this variable, it's not there. We'll broadcast the read miss. So either we'll get the value from another cache or from the lower level, doesn't matter. So then we'll transition to the S state or the shared state. So the shared state basically tells us that we have the data, but this current cache has not modified the data yet. After this, as long as we can just keep on reading, it will remain in the shared state. So basically the format over here is essentially the message that we need to send or the message that we get and the action taken. So if we just want to read and we have a read hit, then we don't have to do anything. We just continue to remain in the shared state. However, if let's say there is a necessity to evict the data, we can seamlessly evict it because we have not modified it. So we will transition to the invalid state, and subsequently the cache might decide to put another line in the place of the current line. Now let's assume that we decide to write to this line, right? So now let's assume that the processor that owns this L1 cache. Well, I'll make one important point 1 minute later, but let me just continue. So let's assume that this processor over here wants to write to this L1 cache. So then what will happen is that since the line is there, we'll have a write hit. But to keep all the other copies up to date, if there are any, we don't know at this point, we just broadcast the write to all the other caches such that they can update themselves. And we transition to the M state, which means a modified state. After this, well, we can keep on reading, and if there is a write hit, which means that we want to write, well, we just happily go and write, and we broadcast the write such that all the other copies can keep themselves updated. Now the same thing, well, similar things happens over here. If we decide to evict this line, since we have modified it, we need to write it down to the lower level. So we do what is called a write back to the lower level cache. In this case, it's an L2 cache. And we transition to the I state. The reason we do that is because we don't want our updates to get lost. So it is possible that another cache has a copy of the latest data, but we don't know that. So to be on the safer side, we write it back to the lower level. So one transition we are missing, which is assume that the line is an invalid state, but there is a write miss, which means we want to write a line and the line gets populated over here. Then we broadcast a write miss on the bus. And so let's see. Let's assume there's one L1 and one more L1, right? This is the bus and one more L1 cache. And let us assume that L1 wants to write to X. It wants to set X to 5. So what does it need to do? Well, if it has X, then it can happily write 5 over there and broadcast the write. That is fine. If it does not have X, what is it supposed to do? This is one of the most important points where students make mistakes. And recall that we had a similar discussion when we were discussing caches. So let me first sort of bring in this discussion. This is the point that I was trying to make a minute ago, but I sort of held myself back because this is the most complicated aspect of the protocol. So it would be I thought it would be desirable to discuss this at the end. So what I'm essentially trying to say is that let's assume an L1 cache. So in the L1 cache, assume that the line size is 64 bytes. When we do a single store, and if it's a 32-bit address, if it's a 32-bit system, we might write to only 4 bytes. But what we do is that the L1 actually requests the L2 cache, right, for 64 bytes. We get the entire block from the L2, and then we put this block in L1. And in this block, we write to some, one of the four, so, one of the sequences of 4 bytes within this block. So if the block is 64 bytes, we might write to this chunk of 4 bytes or we might write to this chunk of 4 bytes. But the main aim is to get the block first. So the question is, why did we do it? We had answered this question in chapter 9, but let me answer this question once again for you. So the answer to the question was that, well, we cannot directly go ahead and write it because, even in an empty block, if we can't just go ahead and write 4 bytes because we need to then keep track of which 4 bytes were written, and this can get very complicated. That's the reason we first fetch the old copy of the block and then make a change on it, which is write to, the 4 bytes that we want to write to. So this is why we fetch an entire block in one go. So same logic holds over here, that assume that I am in the invalid state, which means I don't have the data. Then I put in a write miss on the bus. So I get the block either from another sister cache or from the lower level. Right, so I basically broadcast a write miss and I get the block from somewhere. And after that I perform the write. So it's exactly the same logic, that I need to get the old copy of the block first and perform the write. Alright, so I'm deliberately going slightly fast here because this logic has been discussed threadbare in chapter 9. So you can go back to it. But the important point is that whenever we want to write, we first get the entire block, which can be 64 bytes or 128 bytes, and then we write to 4 bytes or 8 bytes within it. So there are two, so this is the basic protocol. So let me again clean up the screen. There are two things. So whenever we do a write, we have to broadcast the data. That's the reason it's called a write-update protocol. This is, technically speaking, not a very good idea. The reason for this is that you can have a lot of writes in a program that will lead to a lot of traffic on the bus. There's one more blue box that I've added that says that for any write message for us received, sorry, not messages, it should be message received from another cache via the bus, right? So I receive any write message in either the shared state or in the modified state via the bus, which means another cache is writing to it. I simply update my value. So this is the update in the write update protocol. All right. So the more details are there in the book, but we can proceed for the time being. So what is the main problem in the write update protocol? The main problem is that we need to broadcast data on every write, which is technically speaking not the right thing to do because we might have too much of traffic on the bus. And also the bus is a single shared resource. The bus might get clogged and that might lead to additional slowdown. So there is basically a need to have a protocol which is lighter in terms of traffic. So here is a basic insight that we use to create a new protocol called the write-invalidate protocol. Not write-update, but write-invalidate. So let us assume that if a block is there in the M state with some cache, you know, so we are sort of creating a new protocol. So new protocol, the states mean different things. So let us assume that if a block is there in the M state with some cache, then no other cache contains a valid copy of the block. We didn't make this assumption in the write update protocol, but let's make it now. That, if it can be there in the M state, one block, right, one block address can only be in the M state in only one cache. So this we will show will ensure that we can write without any broadcasting. The rest of the logic remains, well, more or less, I wouldn't say the same, but more or less the same, right? I would maybe add more or less over here, sort of to make things slightly clearer. So one more thing, so we are assuming that our system diagram is like this. Actually, let me just go back. We are assuming that our system diagram is like this, that we are implementing cache coherence at the level of the L1 caches, and below the shared bus, we have a large L2 cache. But this need not be the case, so we can implement coherence technically speaking at any level. So we can also have private L2 caches and implement coherence between them. It is just that it's typically not done, and but it can be done. There's nothing that is stopping it, so we can implement coherence at any level. So that's, since we're using L1, I've used the words processor and cache interchangeably, but in a different version of slides, this should actually be caches. So this I'll update for, but for the time being, let's assume that the word processor and cache is being used interchangeably. Even though, to make it generic, I will remove it. All right, so let's look at the write-invalidate protocol. So the write-invalidate protocol has a similar thing. So we're looking at a similar MSI protocol over here, which is nice and simple. So in this case, what we do is we do exactly the same thing. With every tag entry in the tag array, we associate a state. Since there are three states, we need 2 bits to encode the state. So we have M, S, and I. So this is a state transition diagram for actions taken by the processor, right? So basically, when a processor sends something to the L1 cache, what happens? So we of course always start in the I state. So let's assume that we are trying to read a variable. We don't find it. So we have a read miss. So we broadcast the read miss on the shared bus. And if any other sister cache has the data, it sends the data to us. So we transition to the shared state. The shared state means more or less the same thing in both the protocols. So from the shared state, if you want to evict the line, we can always do that because we have not written to the line, the block, right? Line and block again being used interchangeably. So since we have not written to the block, we can happily evict it, which is this point. The second point is if we want to read it, we can always keep reading, right? There is no problem in that. Now let's assume that we want to write to this particular block. So in the write-invalidate protocol, what we have to do is we have to, in a sense, seek permission from the rest of the caches to write to this block. So if we want to write, of course, it will be a write hit because the block is currently there with this cache. So we will then broadcast a write message to the rest of the caches. So if this is, one cache over here, C, and all the other caches, C1, C2 to maybe Cn, we want to write over here, then we sort of send the write message to all the other caches that we want to write here. So when we write, we also transition to the M state. So recall the assumption that we have made that any line can be in the M state in only one cache. So what the other caches will basically do is that they will invalidate the line or essentially set the value of their line to I, right? Set the state to I. So they'll make a transition. If there's another cache has it in the M state, it'll go from M to I. If another cache has the line in the shared state, it'll again go from S to I. We are basically ensuring that no other cache has a copy. After doing that, once we are in the M state, we can keep on reading and writing. Mind you, without sending, so these are empty, without sending any message. So no messages are sent. Once we are in the M state, we can read and write as much as we can. Because we are sure that no other cache has a copy, so there is no need to maintain any kind of coherence. Now, when we are in the M state and we evict the line, which is this, since we have written to the line, the same logic applies. We write it back to the lower level. And similarly, we will transition from the I state to the M state when we are trying to write but we don't have the line. So we'll send a write miss request. So the write miss request will first go to all the caches. If any of the cache has a copy of the line, it will transition to the invalid state and give us the block. Exactly the same way that we did it in the write update protocol. Then we uh, basically take the block and we write to it. So as you can see, the rest of the protocol is more or less the same. There is no major differences as such. It is the main difference, if you actually think about it, is the way that we handle writes in our system. In the write-invalidate protocol, when we want to write, we transition to the M state, and after that, we don't send any messages. So that's one more important difference that, when we write, we don't send any messages, so there is no update that is happening. And that is because we are guaranteed that no other cache has a copy. So if we take a look at the next diagram, which is a state transition diagram for events that are received from the bus. So let's look at the shared state first. So the shared state literally means shared, which means that the same variable can be there in multiple caches in a read-only mode, which means the caches can read it but cannot write to it. So X can be here, here, and here. So their respective processors can read the value of X. There is no problem. Now assume that there is a new cache which wants the value of X. Well, it'll then send a read miss message on the bus to all the other caches. One of the caches will, whoever gets access to the bus first, will send the value of X to this cache, right? So this is how we respond to a read miss. However, if let's say that another processor just writes, uh, another processor simply writes to this particular line, right? Wants to write, seeks permission to write. So in this case, if we just go back to the previous slide, the messages that are sent on the bus are either write miss, means that I don't have the data, so send the block to me, or write hit means I have the data, but I have the data in the shared state, so I need exclusive access. So then a write hit message is sent. So, sorry, this should be write hit. So what will happen is that if a block is in the shared state and it gets a write miss or a write hit message on the bus, then the first thing is it needs to transition to the I state, which basically means that if another cache is writing, the current cache has to throw the data out. Now, there are two kinds of messages that can come from the bus. So if a write miss message is coming, this means that the writing processor does not have the block. So the block needs to be sent. So the block will be sent. If a write hit message comes, it means that the other cache has the block, but it does not have the block with the write permissions, which means it's there in the S state, not in the M state. In this case, nothing needs to be done. We just need to transition to the I state. Similarly, if I consider the M state, the modified state, there are two kinds of messages that I can get. I will never get a write hit message here because no other cache can have another copy of this block, but I can get a read miss and a write miss. So if I get a read miss message means some other cache is trying to read this. So what I can do is I can send the data. Okay, so I can send the block and also transition to the S state. The reason that I do it is because it is not possible that one block can be there in an M state in one cache and an S state in another cache. So in the M state, it can be there in only one cache. So that's the reason. So it's sort of something like this, that if I have this line in the M state here and this line here in the I state, and subsequently from I try to move to the shared state because I want to read. It is not possible that the same block will be there in the M state in this cache and in the shared state in this cache. So this also needs to transition to S. And since this block is trying to read, well, we need to send the data, and also we need to do a write back to the lower level, which is L2. And the reason we do that is basically because we want to seamlessly evict data from the shared state. So if you would recall, from the shared state, when we want to evict data, in a sense throw data out, what we do is that we just throw it out. We don't do any writing. So we want to do exactly the same. So whatever new data we have written in the M state, we'll ensure that it is up to date with the L2 cache, the lower level. And that's the reason we do a write back and also send the data to the requesting cache. Now assume that another process has a write miss. So write miss basically means that it is trying to write. So it will transition to the M state. So in this case, the only thing that needs to be done is we need to send the data to it such that it will at least get the entire contents of the block and it can overwrite it. So the summary of our discussion is somewhat like this, that as compared to the write update protocol, which sent data on the bus all the time. Whenever there is a write, we used to broadcast the data to all the other caches and they used to update themselves. This per se has a lot of traffic and a lot of power consumption. This is inefficient. What is much better is our current approach, our MSI approach, and the important insight in our MSI approach is that if let's say a given block is there in the M state with some cache, no other cache has a copy of the block in any valid state, which is S or M. So this ensures that if we write to it, we can keep on writing without any interference. So we then have the shared state, but shared state means that we have read-only access to a block and we cannot write to it. To write to it, we have to transition from S to M. And when we do this transition, we send write miss and write hit messages on the bus. So this ensures that other caches that might have a copy of the block will all transition to the invalid state. Now the question is, now the question is like this, that what is the, proof of correctness of the write-invalidate protocol? Does it follow the cache coherence axioms, which are that write completes, the completeness axiom? So let's look at this. So for a write to complete, which means that I issue a write and ultimately it has to happen, what do I need to do? What I need to do is that first I need to get access to the bus, right? And I need to put either a write hit or a write miss request on the bus. After that, I'm more or less done. So of course, since if the bus is fair in the sense it ensures that no request stars forever, then a write will always come on the bus and it will always succeed. So this is guaranteed. Now let us look at the order axiom, which says that writes to the same location are seen in the same order by all the processors. So the order axiom is also maintained, the reason being that consider any location, consider variable x. So the cache line that contains variable x, for any request to write to it, it needs to set it in the M state, modified state. So say one cache can only have the line in a modified state and no other cache will have a copy. So if we just track the order in which caches get this line in the modified state, then this order is globally visible because you essentially go to the modified state by sending messages on the bus, which is a central resource. So pretty much the order in which we enter the modified state for this particular line determines the order of writes to this particular memory location, the memory location containing X. And this is same across all processors. So all the processors will see the same order of writes to the same location. So this axiom also holds. So now we have looked at two very basic protocols, two very basic MSI protocols, write update and write invalidate. Write update is somewhat expensive in terms of messages and power. However, it is simple. It just keeps multiple copies and updates them. Uh, on every write, of course. Write invalidate is slightly more complicated, not very complicated though, and it has a far fewer number of messages. In that sense, it is more efficient and is typically preferred. So now I'll give you a very brief cursory idea of another protocol called the directory protocol. So we'll not discuss this. I'll just give an idea that something like this exists. So what we have is that all the messages sent on the shared bus are essentially broadcasts, be it a write hit, write miss, read miss, and these are expensive. Also, if we have 32 or 64 processors and one shared bus, the shared bus will become the bottleneck. So the insight that we see, that we get from most programs, is that most blocks are cached by a few caches, not very many. So let us have a directory, which is a special structure that maintains a list of all the sharers for each block, all the caches that contain that block. Then let the directory send messages to only the sharers for a block when there is a state change. And of course, we can dynamically update the list of sharers. So this per se is a far more efficient protocol because it avoids the broadcast altogether. But this is better taught in an advanced course on computer architecture. Alright, so we have done most of the heavy hard work of looking at MEMD multiprocessors. So we have looked at coherence, we have looked at consistency, very difficult stuff. We have looked at sequential consistency, we have looked at weak consistency, we have looked at the write update cache coherence protocol. We have looked at the write invalidate cache coherence protocol. So we have genuinely done a lot of hard work. And all of these are actually, advanced concepts in computer architecture. But the reason they need to be taught to students now is because the era of parallel processors or multi-core processors has begun. In fact, it has begun long back, at least 7 or 8 years ago, at least in 2010. But now, no undergraduate curriculum is complete, at least without some understanding of how parallel processors actually work. And in any decent understanding, definitely it is necessary for a student to understand sequential consistency, weak consistency, and these write update and write invalidate cache coherence protocols. So now we'll go to fundamentally simpler stuff, multi-threading vector processors and interconnects. So this we will cover in the subsequent lecture.